All right, so let's do a little bit of a lesson on chapter 17, which is electric potential. And so it's the continuation of electrostatics, electrostatics being static electricity. Some of the content that is in this chapter in the textbook I'm not going to be covering because it goes above and beyond what we need for AP Physics 1. That would be more AP Physics 2 as you start to dive more in depth into that. I will touch on it slightly, but let's just kind of cover the basics here. So let's look at this this little setup here where we have two different plates. So we have a plate here that is positively charged, and we have a plate that is negatively charged. And so it should stand to reason that any sort of positive test charge that we put at the within these two plates, that towards the positive plate, it wants to accelerate and go towards the negative plate. So it stands to reason that there would be a high potential energy here and a low potential energy here, which is what is expressed here. But you'll notice it also says high potential versus low potential, and at first you would think that that is referring to potential energy. It's not. So right now I have to be very clear about something, that the idea of electric potential energy and electric potential are different. Okay, so that is an important distinction to make. So just have that in the back of your head, and I'll get to that in a minute. So the change in potential energy between these two positions, which keep in mind, that is the same thing as work, right? It takes work to take this charge and push it up to this height, if you will. And I'm going to use that reference more than once. So we're going to push it up to this higher potential position, and that takes work to do. And work is equal to the change in energy. Now remember, technically, work is equal to the change in kinetic energy, but I'm just looking for the magnitude here, not to the direction, and so effectively I'm just concerned about the value. And this is equal to the charge times the electric field times the distance between the two plates, or the distance between charges, if that is what's causing the electric field. This is what's kind of flipping the signage, but I'm not really terribly concerned about that. Just that the energy, potential energy of the system is equal to QED, and that's the way it's usually expressed. Voltage, otherwise known as electric potential. Now those aren't actually synonyms, but I treat them like they are because they effectively are. Electric potential is measured in units of volts. The idea, or the term voltage, is equal to the difference in electric potential. So let me go back to the previous slide. Here we have a low electric potential. That's why this says low potential. Oftentimes the word electric is just taken out of it completely. So this has a low electric potential. We push it up to here, it has a high electric potential. The difference between those two electric potentials is known as voltage. So this is often called a voltage drop. That's often what is referred to as a voltage drop, especially when it happens across some sort of resistor or some other device. So voltage is equal to the change in potential energy, or it's the potential energy per charge. It's actually not even necessarily change in potential. No, it is. So it's the potential energy per charge. So there's some analogies that will come with this, but I'll get to that from a conceptual stance in a little bit. So if the charge is 1 coulomb, okay, and you move it to a position where it now has 1 joule of energy, then it would have 1 volt. Okay, so that's 1 volt is equal to 1 joule per coulomb. And then all this other mathy stuff going on here, let's go ahead and take a look at that in order to see what's happening. So we're just expressing that the voltage between those two different positions is equal to the change in potential energy per charge, which is the same thing as work per charge, right? And so that's all the stuff that I had essentially been expressing. So let's look at this analogy between height and voltage, or electric potential. So I'm just going to, for the most part, I'm going to call this voltage, but you should know that electric potential and voltage are effectively synonyms. Do not get confused between electric potential and electric potential energy. Those are not the same, okay? Those are not the same. Electric potential is equal to electric potential energy per charge. I know that's confusing. You have to make an extra effort to keep that straight. So the electric potential, otherwise known as voltage, is effectively synonymous to height when it comes to gravitational potential energy. So as you lift this thing higher, it would have more potential energy. As you move this object, it's going to have more voltage. So since voltage is the potential energy per charge, as I lift this thing higher, okay, so height is similar to the voltage, okay, height is synonymous to voltage. As I lift it higher, it's going to have more potential energy per kilogram, okay, just like this has more potential energy per charge, okay, so mass and charge are synonymous, and height and voltage are synonymous, okay. So here is the equation I'm going to give to you guys, where voltage is equal to K times Q over R, but let me show you how we get there. So since electric field is force per charge, okay, from our chapter 16 lesson, electric field is force per charge, and force is K times Q1 Q2 over R squared. We often express Q2 as being a little q, because we will generally express that as being the test charge, which is what this one here is. So this is the test charge. And when we substitute F in over here, we wind up getting this equation, right? This is again from a little bit of a remembrance from chapter 16. So pull out those member berries, eat a few, and remember that electric field is K times Q over R squared. You can go ahead and enjoy that South Park reference later. So, here is what I'd like to express, is that since, if I can do a little bit of writing, since electric field is force per charge, we can say that, let's see here, work is equal to force times distance, and so then that means that force is equal to work divided by distance. Remember that work is the same thing as the change in potential energy. And actually, you know what? This is even getting ahead of myself. Let me actually hold off on that for a minute. Yep. Let me hold off on that for a minute. Yep. Let me hold off. Yep. In fact, let me pause. All right, kind of get myself a little bit mixed up there, but let me kind of correct myself a bit. So I was actually kind of going off of some notes, and but here's what I'd like to express, is that, so electric field is K times Q over R squared, but electric field, as we had expressed a little bit earlier here, right here, electric field is the voltage divided by the distance. So let's put those two things together, right? So when we set these two equations equal to each other, then this right here, this distance, this is effectively the same thing as our value of R. It is the distance between 2-point charges, or it could also be the difference between the two different plates. So because those two things are the same, we have the voltage over D, but remember D is the same thing as R. So let me go ahead and express that instead as a value of R. So velocity over R equals K times Q over R squared, and so one of the R's will cancel, and I'm left with that the voltage is equal to K times Q over R. Remember that K can also be expressed in these terms, where epsilon naught is the permittivity of free space. And just kind of give you a little bit of a background there, the permittivity of free space basically has a lot of reference to it refers a lot in terms of like how much resistance there is within a vacuum, okay? So if I have these two charged plates here, where are they? They're right here. So if I have these two charged plates, the electrons, remember that the protons that are in the metal, those are going to stay in place. Those are part of the nucleus of the atoms. Those are not going to move. But the electrons can somewhat freely move, especially considering that it's a metal conductor. And so the electrons, which are freely able to move, why is it that the electrons don't just jump over across this empty space here and jump to the other plate? What is preventing that from happening? Well, there's some amount of electrical resistance of the vacuum itself that is between the two plates. Or if it's air, air itself has its own electrical resistance. So the air acts as a bit of an insulator. Even if you took all the air out, the vacuum of space itself would act as a bit of an insulator, which basically comes down to that idea of permittivity of free space, which is a large part of the reason why this is mathematically represented in this way, because the epsilon naught, the permittivity of free space, that itself kind of represents that electrical resistance. Besides the fact that this has a bit of a mathematical application that that is unnecessary for us at this point. Okay. I think, what I was trying to show you earlier, which I think I might get back into, was where this equation comes from, and I think I'm going to go ahead and do that. So let me get back to that for a moment. So remember that electric field is equal to force per charge. Right? This is what I was going off of my notes earlier, but I got myself mixed up. So electric field is force per charge, and of course, remember that work is equal to force times distance. We can rearrange that so that way force is equal to work divided by distance. And then I can do a quick little substitution where the electric field is equal to work divided by distance times charge. This is the same thing as potential energy, right? So this is the same thing as the change in potential energy over distance times charge. And if I were to just multiply each side by Q and D, then I would say that the change in potential energy, which is what this is, right? The change in potential energy is equal to Q E D. I changed the order a little bit because this is usually the way it's represented, but it's all the same. Okay. So that's where that comes from. Okay, let's get into capacitors a little bit, which is part of the stuff that doesn't really get covered on the AP test for AP Physics 1, but I'd like to at least touch on it for a brief moment. If there is anything, I'm not sure whether they cover this equation or not, but I like to give it just in case they kind of decide to throw that in. And so I think that the idea of a capacitor, they want you to understand the idea of a capacitor. I'm not sure that you have to do really any calculations with a capacitor, but just in case you do, this would be the equation you'd use, where Q is the charge, C is the capacitance of the capacitor. It basically refers to how good it is at being able to hold a charge. The higher the capacitance, the better the capacitor, the more ability it has to hold a charge. And then of course this is the voltage of that capacitor. So I'd like to talk about how capacitors work because it's really neat, and it's something that you guys would really find useful into the future. So here's what's happening. We have a battery, and this, by the way, is the circuit diagram of a battery, and this is the circuit symbol of a capacitor, and then the line between them just represents a wire with an electrical resistance of 0, meaning that it's a perfect conductor. So here we have this battery. The big end here represents the positive end of the battery. The small end represents the negative end of the battery. It will always be that way. Now, the negative end of the battery pushes electrons in this direction, and those electrons go up the wire towards this negative end of the capacitor, and electrons will start to collect on this negative end of the battery, of the capacitor. So the electrons will collect. And then, as a result, think about what happens to the electrons that are on the other plate. Okay? Any electrons that are on the other plate, don't they get repelled, right? If there's a collection of electrons, right? So there's a collection of electrons that are here on this plate. And as they build up, because these two plates are fairly close to each other, the electrons that are on the other plate will be repelled, and they'll move down the line. Okay, so electrons will move down the line. The closer these two plates are to each other, the more these electrons are going to be repelled, right? They're like, oh my god, these electrons are way too close. I'm going to push away. And they'll go farther and farther down the line. If you were to then cut the cord, right? You actually cut the line, then what's going to happen, in fact, let me actually erase this part here. What would happen is you would actually have a capacitor. Okay, so let me draw the capacitor plates. I'm going to put them in different colors. And then this is the wire coming off of that plate. Let me kind of join those together. So we have a wire coming off of the other plate as well. Join that together, if it'll let me. And hopefully I did that right. Good. Okay. So I have the ability to move these plates closer and farther apart. Let's start with them fairly far apart. So we have
Mr. Bulis, it's like too high. We can't see the drawing.
Thank
Can you
you
move
for letting me know.
down?
Yeah,
Thank you.
sure. A little better? It's just on the edge. Just on the edge, right there. So I'm on the edge. So it's just, some distance apart. Here's your battery. You've charged up the red plates. The red plate has become negatively charged because electrons are pushing up on this plate here, and it's pushing the electrons away over here. Then you literally cut, right? You cut away the battery, and you're left just with this capacitor. Now, if you wanted to, what you can do is, because the electrons want to go from this plate to the other plate, what you can do is you can then take a wire and then put some sort of light bulb in between. So let me actually draw a cheesy light bulb. And when you complete the connection, this light bulb is going to light up because the electrons are going to flow back through, go through the light bulb in order to try and get to the other plate. So that's essentially what a capacitor is. And you're like, well, what's the difference between a capacitor and a battery? Well, they can effectively serve the same purpose. You actually can use capacitors in place of batteries. The difference is that the capacitors, batteries want to cause a chemical reaction at a very regular rate. It's very predictable. They're not going to overload the system necessarily. Versus a capacitor, those electrons want to jump from one side to the other immediately. So basically, you blow up the light bulb, or blow up the motor, or whatever it is that you're driving. Now, you can put a resistor in there in order to slow the flow down, but that is essentially the difference between a battery and a capacitor. Also, the difference is that a battery doesn't have has more energy storage than a capacitor does. So per weight and per volume, the energy density of a capacitor is not anything close to that of a battery. But that's where technology is changing, and that is something that I want you guys to be very aware of. So how do you increase the capacitance of a capacitor? So if I take this away, and let's bring this thing back in, so we charge it. Now, you should recognize that if we bring the two plates together, and you go to actually charge this thing together, so you connect the circuit, because the two plates are very close together now, the the negative plate, the electrons that are on the negative plate, are going to push the positive plate electrons farther down the line. So effectively, the entire idea behind capacitors is to try and get the two plates so close together, they're as close as possible. And you want to put something in between them that is a very, very good insulator that will not allow an arc to occur between the two plates. If an arc occurs between the two plates, that's it. It's a terrible capacitor. So if too much charge is built up on a capacitor, that could happen. You can arc through the insulator because the insulator just can't hold back all of those electrons. So the technology right now is in an effort to try and make the two plates as close to as possible without letting them touch and without letting an arc occur between the two plates. The material between the two plates isn't just called an insulator, it's called a dielectric, and it will actually produce its own induced charge inside of that material itself. So the technology intent right now is to actually make nanofilms that will make the two plates literally 1 or 2 atoms apart and not allow an arc between them. And then you stack these on top of each other so they're just layers and layers of capacitors. So the idea behind a so-called supercapacitor is to get a capacitor that has such a high capacitance that it will have a similar energy density to that of batteries. So where I think this will apply for you guys in the next 20 years or so, I would say that I would expect to see cars in the next 20 years that have a hybrid system of batteries and capacitors, so that when you go to charge your car, it will take literally 5 minutes to charge your entire car, because capacitors can charge extremely quickly, and as long as they can get the technology to have them hold more charge, problem solved. Now there's more to capacitors than just powering things. Capacitors are put into circuits in order to serve a purpose. So it takes a certain amount of time for a capacitor to charge, which is something, it's a big part of the math behind them. And so as the capacitor charges and as it gets to full charge, because of the negative and positive plates here, an electric field is produced. Okay, so think about this. So you charge a capacitor, and let's say it takes 1 second to charge a capacitor. Then, after 1 second, the capacitor is effectively fully charged. And at that point, there's an electric field produced. Now, if you remember me talking about semiconductors can change their electrical resistance due to an electric field. So what if we had a material here, what if I had a wire here, just nearby, I had a wire here that was made of a semiconductive material. When this capacitor gets fully charged, it produces an electric field, where this wire, which is normally an insulator, now because of the electric field, it now becomes a conductor. Now there's a flow of electricity through this wire, and hey, what if the wire is actually connected to the same circuit as the capacitor? So as electricity flows through this wire, the capacitor gets discharged, which means that the electric field goes away, which means that all of a sudden there's no longer any electricity flowing through this thing. And now the capacitor starts to charge up again, and then wire flows through again, and then it gets discharged. So you would essentially have a way of making a clock, right? A 1 second, right? You have a timer. Like every 1 second, this thing is charging and discharging. So I hope that you see that capacitors, in conjunction with semiconductive materials, can produce these sequential sort of events that occur within circuits, and you can see how it can really expand from there. So capacitors are huge in any sort of circuitry, and of course I think that they're very, very huge in terms of future energy storage. So that's something to really pay close attention to. Again, the idea of capacitors I think is most important. This equation is the only thing that maybe you would have some knowledge on, but I'm not terribly concerned about that. Capacitance is measured in farads. And then the other issue too is I've been talking about the direction of the electrons. Basically, from now on, for the most part, as we move forward, we're going to be talking about conventional flow. So yes, electrons are flowing in this direction. However, we're going to talk about the positive flow of electricity. Now, to express that, if you were standing here, if the electrons are flowing to the right, I guess my little guy is off the screen. So if I have electrons that are flowing to the right, in your perspective, do you understand that to the left, that this area is becoming more and more positive? So we have a positive flow to the right and a negative flow to the right. Even though the positive charges aren't actually moving, all motion is relative. Remember that. So as the electrons are moving to the right, relative to them, the protons are moving to the left, and so we can actually talk about the positive flow. If you don't like that, don't blame me, blame Benjamin Franklin for getting it all wrong in the first place. Okay? So, that is my sort of quick little overview of chapter, 17. Remember that height is analogous to voltage, and potential energy is different than electric potential. So I'm going to leave it at that, and I'll kind of end things through there.